Hello, everyone, and welcome to another AP Chemistry virtual lesson. My name is Michael Faribaugh, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. The focus of the lesson today, as well as the lessons all of this week, is going to be on AP exam practice. Just want to remind you that you can go to apstudents.org/exams2020 to get more information about specific details regarding the AP exams online. For AP Chemistry, your exam is on May 14th. So again, there's going to be 2 free response questions. The first one will be 25 minutes, the second one for 15 minutes. And just to remind you that you can go to the College Board website. You can log in at myap.collegeboard.org. And then once you log in, you can take a look at AP Classroom. So when you see your classes in AP Classroom, while your teachers may assign specific practice problems for you all to do, there are optional practice problems for you all to click on and take. So I want to just remind you about that. So if you log in and you click on AP Classroom, you will see a progress tab. And at the top on the far left, it says, click here for optional student practice. You will also see a link to all of the AP live classes. So you can click on that to access the YouTube channel. If you click on the optional student practice, then you should see a variety of free response questions. And again, they'll be labeled, and you can click on any one of them. So when you click on that particular to begin the question, the FRQ, the free response question, then you can actually read the question, enter your response in the box, and then here's an interesting thing you can do for these optional AP practice questions. You can click submit, and once you click the submit button, it's going to respond. You say yes, but then a screen will come up saying, do you want to submit now, or would you like to review how this question might be scored on the AP exam? So you can actually say, click yes, review, to see the scoring guidelines. Now, once you look through the scoring guidelines, then you can decide to modify your answer. And then when you click submit, you would say, okay, I've already reviewed, click submit, and then no, submit now. And then your teacher will have access to that question you submitted. So again, those are good practice problems. Okay, so again, you would go to log in. That's myap.collegeboard.org. Click on AP Classroom, click on the optional student practice problems, and then you can work on that. All right, so for today's lesson, I'm going to give you several AP practice questions. Hopefully you have access to a periodic table and scratch paper and something to write with. And again, please feel free to pause the video, and then you can solve the problem, and then click play when you are ready to check your answer. Okay, so for today's lesson, I strongly encourage you to solve the problem on your own before you simply just listen to my explanation. So for this first free response question, it has 5 parts. So parts A, B, C, D, and E. This is the first screen. This is parts A and B. And then this is the next part. This is parts C, D, and E. So again, I encourage you to try all of these parts of the question. And then when you're ready to see if your answer matches the correct answer, then feel free to click play and continue watching. Okay, so I'm going to assume that you have already had a chance to answer this question on your own. If not, feel free to pause the video and do that. Otherwise, if you're ready to take a look and see if your answers match the correct answer, we're going to go ahead and get started with this first free response question. All right, it says a sample of a pure gaseous hydrocarbon is introduced into a previously evacuated rigid 1.00 liter vessel. The pressure of the gas is 0.200 atmospheres at a temperature of 127 degrees Celsius. So part A asks you to calculate the number of moles of the hydrocarbon in the vessel. So since we do not know the chemical formula of this hydrocarbon, we cannot use the periodic table. We don't know how many grams there are. So in fact, we're going to have to get our information from what's given to us so far. So we have the ideal gas law. I'll remind you that you do have access to an equation sheet. So on the AP exam, if you have already accessed the equation sheet, you can find not only the ideal gas law, but other gas equations involving pressure, and there's a conversion from Kelvin to Celsius, and there's information about the kinetic energy of the molecule as it relates to the speed. So all this information is available, and then there are 3 different values of the ideal gas constants. You can think about which particular one you'd like to use. Since we were given pressure in atmospheres, it would make sense to go ahead and use this particular one. So I've got PV equals nRT. I'm going to solve for moles. And I already see that I have a pressure, I have a volume, and I have a temperature. So I'm going to go ahead and set this up, PV over RT, where R is 0.08206. Before I continue to actually do this, I want to go ahead and comment something about this particular question. I'm hoping that you guys have already noticed this, but what I have just done, and this is intentional on my part because it's a very common student mistake, is that I have intentionally made a mistake in setting up this question. So I'll give you a moment to see exactly what I did wrong. I kind of mentioned it briefly with respect to the AP equation sheet. So you'll notice that on the AP equation sheet, they do tell you how to convert from Celsius to Kelvin. And as you can see, Kelvin is featured along with liters, atmospheres, and moles. So hopefully you realize that if we had plugged in 127 into our calculator, that would have been the wrong answer, because 127 Celsius, it's actually 127 plus 273, which works out to be 400 Kelvin. So again, the atmospheres will cross out in terms of a unit, as well as liters and Kelvin, and then our answer will come out in moles because we have inverse moles on the bottom. So if you do this math, 0.2 times 1 divided by 0.08206 divided by 400, this is the correct answer to part A. I'm going to go ahead and round this off to 3 significant figures based on the measurements that I see in this problem that also have 3 significant figures. So I write my answer as 0.0609 moles, or you could say 6.09 times 10 to the negative 3 moles. All right, on to part B of this question. It says that oxygen, O2, is introduced into the same vessel containing the hydrocarbon. And after the addition of the oxygen, so we already have a pressure of 0.2 atmospheres from the hydrocarbon alone, the total pressure of the gas mixture is 1.4 atmospheres. Calculate the partial pressure. Now, this is a very easy question in terms of math, in terms of concept, but I'll go ahead and point you back to the AP equation sheet, and you can see that the total pressure of a gas mixture is simply the sum of the partial pressures of individual gases in that mixture. So we have 2 gases in this mixture, the hydrocarbon and the oxygen, and the total pressure is 1.4. The pressure of just the hydrocarbon alone is 0.2, so the difference is 1.2 atmospheres. So we have now answered part B. On to part C. The mixture of the hydrocarbon and oxygen is sparked so that a complete combustion reaction occurs. Now, we do not know the formula of this hydrocarbon, but we do know that it is going to undergo a combustion reaction with oxygen. So all of the carbon that was present in this hydrocarbon is converted into CO2 because complete combustion reaction occurs. And all of the hydrogen that was in this hydrocarbon, where the subscripts right now are just X and Y, because I don't know what those numbers are yet, all of the hydrogen is now converted into water vapor. And so we have access to information about how much carbon dioxide and water was produced in terms of partial pressures. So we are given that we have a hydrocarbon, it reacted with oxygen, and it produces CO2 and H2O. So part C, use the partial pressures of CO2 and H2O, which are 0.6 atmospheres and 0.8 atmospheres, to calculate the partial pressure of the oxygen consumed. Now, don't confuse this with the answer to part B. In part B, this was how much oxygen was available. But we don't know how much of that 1.2 atmospheres was actually consumed. So the initial pressures of all four gases are the following. We were given a pressure of 0.2 atmospheres for the hydrocarbon. We were given an initial pressure of 1.2 atmospheres for the oxygen. And since that was it, then initially the reaction did not, the mixture did not contain any carbon dioxide or water because the reaction has not occurred yet. At the end, after the combustion has occurred, and we're assuming that complete combustion means that all of the hydrocarbon was consumed, there should be no amount of hydrocarbon left over because it was the limiting reactant and consumed all the way. There's going to be some amount of oxygen left over, but all we're given is that there is oxygen remaining in the container. That tells us that oxygen was the excess reactant and the hydrocarbon was the limiting reactant, but we don't know how much oxygen is left over. So we can't do a simple subtraction based on that. We also know that we have 0.6 atmospheres for the pressure of the CO2 and 0.800 atmospheres for the pressure of the water. So if we know the partial pressure of the CO2, along with the volume and the temperature, so we still have a 1 liter container, we still have a temperature of 127 degrees Celsius or 400 Kelvin, then we can calculate the number of moles of CO2 produced. And this will help us get closer to our answer. So let's go ahead and start with that. Let's use the same N equals PV over RT. We'll plug in the pressure of the carbon dioxide, the volume of the container, which is still 1 liter. We have the ideal gas constant, again, with atmospheres, and the temperature in Kelvin. So this is how many moles of carbon dioxide were produced if I do that math, 0.0183. Well, I can do the same thing for the water. We know the partial pressure of the water is 0.800 atmospheres. So I can solve for moles in a similar way. So I get 0.0244 moles of water. You might be wondering how this is going to help us figure out the amount of O2 since we can't balance this equation. So I'll say it one more time. All of the carbon was converted to CO2 and all of the hydrogen was converted into water. But look at the oxygen. Since there is no oxygen present in the hydrocarbon, then we could convert CO2 into how much oxygen was used and water into how much oxygen was used. So I'm going to go ahead and write a conversion factor that converts from moles to moles. So we're going to put moles of CO2 on the bottom and moles of O2 on the top. We'll put moles of H2O on the bottom and moles of O2 on the top. So where am I going to get these numbers from if they don't come from the actual coefficients? Well, consider that there are 2 atoms of oxygen in CO2. So therefore, for every 1 mole of oxygen that reacts, If we're just focusing on the CO2, that would be 1 mole of CO2 produced. In a separate way, I can focus on the H2O, but there is only 1 atom of oxygen in water. So for every 1 mole of oxygen gas that would be consumed, I would actually produce 2 moles of water. So I'm doing these separately just based on the subscripts in the chemical formulas. So I can do that. And I come up with 0.0183. That's how many moles of oxygen was consumed to produce the CO2. And then because I'm dividing by 2, I get 0.0122. That's how many moles of oxygen would be consumed from just that portion to produce the water. I can add these together. So 0.0183 plus 0.0122. That means that total number of moles consumed to produce this product, CO2 and H2O separately, and then just add them together, is 0.0305. Now, the question was asking how much pressure. They were talking about the partial pressure of O2 that was used up or consumed. So I can go back to the ideal gas law, but this time I'm solving for pressure. I plug in my number of moles of oxygen consumed, same ideal gas constant involving atmospheres, same temperature, 400 Kelvin, 1 liter vessel, and I get 1 atmosphere. So that is the amount of oxygen in terms of pressure that was consumed. So the hydrocarbon went down by 0.2. And of course, the oxygen has gone down by 1 atmosphere based on our calculations on the previous screen right here. So this is the amount of oxygen consumed in terms of the partial pressure. And we already know about the pressure of the CO2 and the H2O. So this was our answer. I'm now going to jump to the official scoring guidelines, and they actually do it 2 ways. So focus on this method first, which is on the bottom. So that's what I was showing you on the screen, that you can take a calculation to get moles of both CO2 and H2O, just converting with the ideal gas law from pressure to moles. And then here was that conversion factor to go from moles of CO2 to moles of O2. That was a 1-to-1 ratio. To go from moles of H2O to moles of O2, that was a 1-to-2 ratio. And they took these number of moles, they added them together to get 0.0305, and then they finished off and solved the problem. Now, I like this other method, which is kind of a shortcut. It's because moles and pressure are proportional. So they took this same 1-to-2 ratio, and they just did that with pressures. So for every 0.8 atmospheres of water produced, 0.4 atmospheres of oxygen would have been consumed. And based on this 1-to-1 mole ratio, for every 0.6 atmospheres of CO2 produced, 0.6 atmospheres of O2 would have been consumed. And so 0.6 plus 0.4 is 1 atmosphere. So I'll go ahead and remove my writing so you can see this better. So 2 ways to do it. Either of these would have been acceptable. Again, the correct answer is 1 atmosphere of O2 is how much the oxygen was consumed in terms of pressure. All right, so now we're on to part D of this question. On the basis of your answers above, and again, here's the information we have so far, write the balanced chemical equation for the combustion reaction and determine the formula of the hydrocarbon. So initially you might think, I don't think I have enough information to do this, but in fact, you do. And the focus here is right here. Look at the change, because as you may recall, whenever we did ICE tables or RICE tables in Unit 7, the change, whether it's in terms of moles or pressure or concentration, has to always be in proportion to the coefficients. So whatever these coefficients are in our balanced chemical equation, they must be proportional to the change in our Rice table, or in this case, the change in pressure. All right, so if that's the case, let's say I go ahead and just make up a coefficient of 1 for my mystery hydrocarbon. Well, hopefully you can see that the change in oxygen is 5 times as great as the change in the hydrocarbon. So 1 is 5 times greater than 0.2, so I'm going to go ahead and put a 5 in as my coefficient. And then as you compare the 0.2 with the 0.6, you can see that the change in carbon dioxide is 3 times as much. Compare 0.2 with 0.8, and you can see that the change in water compared to hydrocarbon is 4 times as much. Well, now that we've done that, 3 moles of CO2 contain 3 moles of carbon. 4 moles of H2O contain 8 moles of individual hydrogen atoms. So we now have our empirical formula, which is C3H8, and you can confirm that this, in fact, is a balanced chemical equation, that we have 3 carbons, 8 hydrogens, and a total of 10 oxygen atoms on both sides of the equation. I will then show you the official scoring guidelines. So one way that they talk about this, there's 2 different solutions, is that the partial pressures, as I mentioned, are in proportion to the coefficients and the number of moles in the balanced equation. Or, and this is kind of a different approach that I did not show you, but they went ahead and calculated the number of moles of water and the number of moles of CO2 like we did earlier, and then they converted them into moles of H and moles of C. Now, when they did that, they then compared the moles of H and the moles of C, and they were able to get a 8:3 ratio based on this comparison. So 0.0183 on the bottom for moles of carbon, 0.0487 on the top for moles of hydrogen, and then they turned that, which was roughly a 2.66 or 2.67 to 1 ratio, into a whole number because you can't have a fraction of an atom. So this roughly 2 2/3 to 1 ratio became an 8:3 ratio. And so they got their formula of their hydrocarbon. Okay, the last part, which was part E, is to calculate the mass of the hydrocarbon that was combusted. So remember, we already know in part A that we have 0.00609 moles. And now that we know the chemical formula is C3H8, all we have to do is use the periodic table to go from moles to grams. So on the periodic table, carbon weighs about 12, and hydrogen weighs about 1. So 3 times 12 is 36, plus 8 is 44. There's the official molar mass using all of the decimals from the atomic masses for C3H8. Multiply that, and we have the mass of the hydrocarbon that was combusted. All right, well, again, I'm going to show you another AP free response question. I strongly encourage you to pause the video. So don't just watch me solve it step by step. Go ahead and take the time to solve this new FRQ. This is part A of this question. I think there is a total of parts A, B, C, D, E, and F. Okay, so there's part A. This is parts B and C. And the rest of the question looks like this with parts D, E, and F. So again, please stop the video, solve this problem on your own, and then when you're ready, you can go ahead and press play to check and see if your answers match my answers. All right, I'm going to start with part A of this question. So we are given that a sample of CH3, CH2, and H2, this is called ethylamine, you don't have to know that, I'm just giving it a name, is placed in an insulated container where it decomposes into C2H4, which is called ethene, and ammonia, NH3. Now we're also given the entropy values. So in part A, we're going to calculate the entropy change. Now, I know that officially the AP exam in 2020 is only going to cover units 1 through 7. I just thought I would keep this question intact, even though it does contain entropy, which is from unit 9. So just kind of bear with me. It's very similar to what you might do for delta H in terms of enthalpy of formation. We're going to do products minus reactants. And when I plug in the numbers for products minus reactants, I get positive 127.2, and the units are joules per mole Kelvin, or joules per mole of reaction Kelvin. Just interesting to note that it's a positive delta S. This makes sense because we go from 1 mole of gas to 2 moles of gas. So it kind of makes sense that the entropy change would be positive as we have more arrangements, more degrees of freedom in 2 moles of gas than 1 mole of gas. All right, so that is the answer to part A. Part B, which is definitely part of the information you should know, this is from unit 6, has to do with bond enthalpies. Now, do not confuse bond enthalpy with the delta H of formation. Okay, so be careful you don't make that mistake. This is not enthalpy of formation. This is about bonds. The delta H has to do with the endothermic process, which is a positive number for breaking bonds, and then the exothermic process for forming a bond. And that's where that minus sign comes from, that the minus sign is attached to the formation of the bonds, because forming a bond is an exothermic process. All right, well, the first thing I'd like to highlight in the table is I have a carbon-carbon single bond, and I only have one of those. That would be 348. I have a carbon-hydrogen bond, and I have a total of 1, 2, 3, 4, 5 of those CH. So that's why I have a 5 right here. And then it looks like I have a carbon-nitrogen bond. I have one of those. And then finally, I have a nitrogen-hydrogen bond. Looks like I have 2 of those in the structure. So if I do all of this math, I get 3,488 kilojoules. That is a positive number. I have not done the bonds broken. So I have not done the bonds formed yet. I'm coming up on that, but I've done all the bonds broken. All right, so moving on to the bonds formed, there is only one carbon-carbon double bond that comes in at 614. We have CH bonds again, and there are 1, 2, 3, 4 CH single bonds. So I've got a 4 right there. Then we have a nitrogen-hydrogen bond. And it looks like I have 1, 2, 3 of those. So grand total. Again, this was a endothermic process. This was an exothermic process. So I'm kind of indicating that I'm doing positive 3488 plus a negative 3439. And it works out to be, if I do that math, I get a positive 49. So my delta H for this reaction based on bonds broken minus bonds formed is positive 49 kilojoules per mole of reaction. All right, I will show you a student answer to this question, which represents a very classic, a very common, a very please don't make this mistake yourself when you take the AP exam kind of question here. So hopefully you can see what the student did wrong. Do they have the 49? Oh yes, but they did it completely backwards. And so they got negative 49 instead of positive 49. So again, don't make that mistake. All right, based on our answer, which is positive 49 to part B, predict whether the temperature of the contents of the insulated container will increase, decrease, or remain the same. Remember that the thermometer is always part of the surroundings when questions like this are being asked. So if heat is released, if energy is released, then the temperature is going to go up for the surroundings. If energy is absorbed. Again, focusing on the thermometer being part of the surroundings, the temperature is going to go down. Now, I know that you're thinking, but when you put a pot of water on the stove, you might be thinking, but aren't you adding heat? Isn't that an endothermic process? This happens all by itself. There's no hot plate, there's no stove, there's no Bunsen burner. If you just mix chemicals together and heat is released, then it's going to get hotter. If you just mix chemicals together and they react and heat is absorbed, then the temperature will show a decrease. So what we're focusing on here is the difference between the system and the surroundings. Okay, this is an endothermic reaction because delta H is positive. The temperature of the contents, which again is part of the surroundings, the thermometer is part of the surroundings, will decrease as the reaction proceeds. Now, to those students that made that mistake I showed you earlier, the AP exam would award credit for someone whose answer is incorrect but consistent with a previous incorrect answer. So for all students that made the mistake in part B and thought it was thought it was exothermic by having a negative 49, which is wrong, they would have lost the point in part B for making that mistake. But if they go on to say that the value of delta H is now negative, the reaction is exothermic, and temperature would go up, they would get credit for part C for an answer that is consistent with the error that they made earlier. All right, so we talked about the temperature goes down, it's endothermic, and now on to part D. This has to do with rate of reaction. So we are told that an experiment is carried out to measure the rate of the reaction, which is first order. They give us information about moles of this chemical. They talk about after 20 minutes, there's a new concentration, calculate the rate constant. You should know, and again, I mentioned this before, we have the AP equations and constant sheet. You should know that there are several equations. This is the integrated rate law equation for a zero order process. This is the integrated rate law equation for a first order process. Now, these are not labeled on your AP equation sheet, so you can definitely make notes on your own equation sheet to remember which is which. And this is for second order. This, by the way, is a half-life equation, but this is only for first order. So we were told that the equation was first order. So we're going to go ahead and use this particular equation, which is the natural log of the concentration of the reactant at time t minus the natural log of the original concentration of the reactant at time 0 is equal to negative k, the rate constant, times t the time. So there is my equation. I was given this number, which was the initial. I was given this number, which was after 20 minutes. And okay, I plugged in some numbers. Now, I'm just going to pause briefly here. I'm hoping that some of you who are really on top of your game are kind of waving your hands at this point and saying, wait, Mr. Faribault, I think you made a mistake. But some of you who might just be listening to this video or watching this video and kind of following along might think that so far I've done everything correctly, but I have intentionally made a mistake here. So I wasn't reading the question carefully. Do you see what I did wrong? Okay, and I specifically circled these two numbers, and I also tried to circle the unit. So we have a difference here between moles per liter and just moles. So if you were not paying close enough attention, you might think that the initial concentration is 4.70 times 10 to the minus 3. But that is the amount of moles. And by the way, we are not, unlike the last problem, which was a 1 liter container, we are not in a 1 liter container. So molarity is moles divided by liters. So the initial concentration is actually 2.35 times 10 to the minus 3 when you do moles divided by liters. Now I can plug in that particular number for my initial concentration into the first order integrated rate law equation. So I'm going to go ahead and take care of this math. I'm going to solve for K. Now the units are nothing. On the left side of the equation, there are no units. When you take the natural log, there are no units. On the right, we have K, and we have 20 minutes. So therefore, the units of K are going to have to be inverse minutes. In fact, for a first order rate law, the units will always be inverse time, inverse seconds, inverse minutes, inverse hours, inverse years, whatever. Okay, so we'll go ahead and finish off this problem. K works out to be negative, well, actually, I guess the negatives go away. So K works out to be 1.88 divided by 20, which is 0.0940. And then again, I have the units, and it said specifically, so pay attention. If they say they want units in the answer, it is possible. I mean, it depends on the AP exam, and I don't know the specific questions, obviously, but if they say include units with your answer, sometimes if it's a 1-point question, you might have the right numerical answer. So like, for example, you have this part correct, but if you either forgot to include the units or you had the wrong units, if it's a 1-point question, you might lose the point for that question based on the units. Now, if that happens to be worth 2 points, maybe it's 1 point for the numerical part and 1 point for the units. It just depends. But if they say include units, then please pay attention to the proper units. Okay, next part of the question, calculate the initial rate. So remember that we're talking about a rate law. And so I'm just going to go ahead and write some rate laws here, using A as a generic reactant. This would be 0 order. This would be first order. So the exponent is 1. And this would be second order. They obviously told us it was first order. So I have to use this particular equation right here to calculate the initial rate of the reaction. So we already have the equation that we're going to use for a first order rate law. In part D, we just solved for the numerical value of the rate constant, and we still have our initial concentration that we calculated earlier. So my units are going to be molarity per minute. That's going to give me the initial rate. So initial concentration times rate constant, and I get 2.21 times 10 to the negative 4, and that's molarity per minute, or moles per liter per minute. All right, there was one more part of this question. Part F, if they plot versus time, so they're going to plot, so time on the x-axis, if they were to plot 1 over the concentration versus time, would they get a straight line? Okay, so 1 over the concentration versus time, would that give me a straight line or a curve? As I mentioned, this is 0 first and second. You should know this, and you can kind of tell from this information here that when you plot concentration versus time, you get that falling straight line where the slope is equal to negative k. If you have natural log of concentration versus time, again, the slope would equal negative k. And if you plot 1 over the concentration versus time, and you get a rising straight line, then the slope would be k. So you should kind of know, in this case, we're talking about a first order, and they're asking, what if you plot 1 over concentration versus time? It doesn't match up. So that's what I said. The plot of 1 over the concentration versus time would result in a curve. Why? Because this reaction has a first order rate law. So a plot of natural log of concentration versus time would have resulted in a straight line. And if the rate law had been second order, then 1 over concentration versus time would have resulted in a straight line. All right, I have one more FRQ to show you. So I'm going to go ahead and go to that next one. This has parts, I think it's A, B, C, D, and E. Let's find out here. We have parts A, B, and C. So again, you can take a screenshot or pause the video on this one. And then we have part D, which looks like this. And then there is one more, which is part E. So at this point, I encourage you to stop, pause the video, work out this particular problem before you go ahead and listen to the official answers. So take the time to solve this problem before you have me spoil it for you in the next bit here. Okay, so I'm going to assume that you guys are ready to check your answers here. All right, we have bromine, Br2, in the table above, going from a liquid to a gas. We have iodine, I2, going from a solid to a gas, and we are given the delta H for these phase changes. Explain why the delta H for the formation of iodine gas from iodine solid is larger than the delta H for the formation of bromine gas from bromine liquid. Now, it says specifically to identify the type of particle interactions involved. If you fail to mention the type of particle interactions involved, then you would not receive full credit. Some students, hopefully not you, think that when you go from a liquid to a gas or a solid to a liquid, that you are breaking covalent bonds, okay, which you are not. But some students don't know the difference between covalent bonds and what I would call intermolecular forces, or IMFs. That's a very common misconception. I talked about this in the Unit 3 video. Okay, so we are talking about intermolecular forces here between molecules, and these are non-polar molecules. It's a diatomic molecule that has the exact same atom. So because they are non-polar, they experience London dispersion forces, or LDFs for short. I think you already know this from chemistry, that going from a solid to a liquid is an endothermic process, and going from a liquid to a gas is an endothermic process. It would stand to reason that it requires less energy to go from a liquid to a gas for a certain substance, but it would require more energy to go from a solid to a gas, because essentially you're kind of combining like the melting and the evaporation and sort of the vaporization in one step by doing sublimation. So it takes more energy to go from a solid to a gas than to go from a liquid to a gas. That's what they were looking for. Another way you could have gotten credit for this question is to focus on the difference in the strength of the London dispersion forces. So because London dispersion forces are largely associated with the size of the electron cloud, bromine, atomic number 35 on the periodic table, has 35 electrons per atom, whereas iodine, atomic number 53 on the periodic table, has 53 electrons per atom. So iodine, I2, the molecule, has a larger electron cloud than the Br2 molecule. So therefore, it's more polarizable and has stronger London dispersion forces. So here's a look at the official scoring guidelines. So you might have said that the reason why it takes more energy to go from iodine solid to gas, as opposed to bromine liquid to gas, is because of the London dispersion forces. Will be stronger in iodine because of its greater number of electrons, larger size, larger polarizability. And then the second reason is that the delta H of sublimation is approximately fusion, which is melting, so solid to liquid, plus vaporization, liquid to gas. So because it involves going from a solid all the way to a gas, it should require more energy to go from iodine solid to iodine gas, whereas with bromine, you are just going from a liquid to a gas. All right, part B of this question says to predict. Again, this is entropy, which I know is not officially on the AP exam in 2020, but I thought I'd go ahead and ask this anyway. Predict, they're not telling you, so predict which of the two processes shown in the table has the greater change in entropy. So again, in terms of gas, you have greater number of arrangements, more freedom of movement from a gas compared to a liquid. Liquid has more entropy and freedom of movement and greater number of arrangements than a solid. So effectively, you are going from a solid all the way to a gas. That is a more dramatic increase in entropy as opposed to going from a liquid to a gas. So the change from a solid to a gas involves a greater change in entropy than the change from a liquid to a gas. And again, to justify your prediction, you can see that you would want to talk about the difference in degrees of freedom as you compare a solid to a liquid to a gas. Entropy is increasing. All right, part C. They're showing you a molecule that is not featured in the table above, and that's IBr. So an iodine bonded to a bromine. It says that iodine and bromine can react to form the compound IBr, iodine bromide. Predict which would have a greater molar enthalpy of vaporization. So IBr liquid or bromine liquid. This is about polar versus nonpolar, but it could also be about the size of the electron cloud. So first of all, you could have said that IBr, which is a polar molecule, would experience stronger intermolecular forces than Br2, which is nonpolar. So the polar molecule experiences both LDFs and dipole-dipole forces, and that would be stronger than the London dispersion forces in bromine. You also could have said that since an IBr molecule has a larger electron cloud, the LDFs, the London dispersion forces, would be stronger in IBr because of its larger electron cloud, greater polarizability. And that's what you can see here on the screen. Two reasons may be given. First, that IBr is polar, and the second, and of course, having the dipole-dipole forces tend to increase the enthalpy of vaporization. And the second is that it should have stronger LDFs because of the larger electron cloud. All right, there was a part D of this question. An experiment is performed to compare the solubilities of iodine solid in two different solvents, water and hexane. So we have hexane, which is C6H14, and we have water, H2O. Now the student adds 2 milliliters of water and 2 milliliters of hexane to a test tube, and then they add a little purple crystal of iodine and shake it up. And the hexane layer becomes purple. So explain why the hexane layer is purple while the water layer is colorless. Again, you should reference the strengths of interactions between the molecules of water and the solvents. I'm sorry, the molecules of iodine and the solvents H2O and C6H14. So one student might have answered the following. The reason why the hexane layer is purple is because the iodine reacted with the hexane. Be careful with your word choice. There is a big difference between dissolved in, mixed with, interacted with, and reacted with. So interact and react are not the same thing. If you say reacted, that sounds like there's a chemical reaction taking place. We're just talking about solubility. We're just talking about solutions. So if you say reacted with, that might cost you a point. The reason why the hexane layer is purple is because the iodine is more soluble in the hexane than the water. And yes, we should know, based on polarity, that hexane is nonpolar. As many hydrocarbons are symmetrically arranged and the dipoles all cancel out, whereas the water molecule, because of its bent shape and the dipoles do not cancel out, is polar. We know that iodine is nonpolar, but it would not be sufficient to say that the reason why iodine dissolves in hexane is that they are both nonpolar, and like dissolves like might be a little mnemonic that you have learned, a little trick to remember about solutions, but this is not a reason why. It's simply a trend. So do not say like dissolves like as your reason or your explanation. Okay, so what's going on here? They say, talk about the relative strengths of interactions between the molecules. So I said that iodine is nonpolar, hexane is nonpolar, and water is polar. And the London dispersion forces between iodine and hexane are stronger than the London dispersion forces between iodine and water. You also might go on to talk about hydrogen bonding, but what that's doing is preventing iodine from kind of getting in there because of the strong hydrogen bonding. So on the official scoring guideline, it said that. It says the entrance of the iodine into the water requires disruption of the hydrogen bonds in the water, which are much stronger than the London dispersion forces in hexane. Meanwhile, the London dispersion forces between iodine and hexane would be stronger than the London dispersion forces between iodine and water. All right, there was also a Lewis electron dot structure you had to draw here for the I3 negative ion. It says the student adds a small crystal of potassium iodide to the test tube. The test tube is corked and inverted several times, and the I3 minus is formed. And it's a linear species. I'm showing 3 iodines in a row with a negative charge on the outside. Now, the valence electrons for iodine would be 7, and we have 3 of them. So 7 times 3 is 21. But don't forget, you also have this negative charge. So we get to add 1 more electron for the negative charge. So the grand total of electrons I have to work with is 22. So with 22 electrons, that's 2 electrons for the shared pair of electrons. That's 4. I'm going to go ahead and satisfy the octet on the terminal atoms, 6, 8, 10, 12, 14, 16. I still have 6 more electrons. I'm going to go ahead and put them on the central atom. Here we have an example of a Lewis electron dot structure which has broken the octet rule for the central atom, but sometimes that happens with hypervalent species, such as this. Final question. In which layer, the water or the hexane, would the concentration of I3 minus be higher? You may remember learning about London dispersion forces and dipole-dipole forces and hydrogen bonding. Hopefully, you also learned about what are called ion dipole forces. So we clearly have an ion here. For ion dipole forces, they have to be interacting with a polar molecule. So the concentration of the I3 minus ion would be higher in the water because ion dipole interactions exist between the I3 minus ions and the polar water molecules, but no such interactions are possible between the I3 minus ions and the nonpolar C6H14 molecules. So like, for example, sodium chloride or table salt dissolves in water, but not so much in something like oil or gasoline or hexane. Same reason. There's no favorable ion dipole forces if you have a non-polar solvent. All right, well, again, that was 3 FRQ practice questions. Hopefully that was helpful to you. We're going to do more FRQ practice this week. Reminder to check out the helpful chemistry resources in the video description. Again, this has been Michael Faribaugh from Albemarle High School in Charlottesville, Virginia. And I want to remind you, especially to tune in tomorrow. Okay, we are very excited. We have a special guest. Okay, tomorrow. We hope that you guys will attend tomorrow to see our special guest. She is the winner of the 2018 Nobel Prize in Chemistry, and she is coming on our program tomorrow to talk to you all and discuss some information about her path and her different things that she can share with you about her journey in chemistry. So if you are interested in watching tomorrow, not just for FRQ practice, but to listen to Dr. Abbott discuss her work, again, the 2018 winner of the Nobel Prize in Chemistry will be joining our show tomorrow. So thanks a lot for watching. We will see you tomorrow.